Welcome to Control Systems Lectures. Before we get started, I want to thank those of you who have subscribed to the channel. And also, whether you're a control student who's hearing this for the first time, or a veteran engineer brushing up on the basics, I appreciate you taking the time to watch this video. And if you find these videos helpful, or if you find that I'm not being clear enough, please leave a comment below and I'll try to address it. But now, on to the lecture. In this lecture, I'm going to describe transfer functions and how control engineers use them to model elements like filters and actuators in order to simplify control system design and analysis. In the simplest description I can find, a transfer function is the Laplace transform of the impulse response of a linear and time invariant system when you set the system initial conditions to 0. Now, unless you're already familiar with transfer functions, I'm betting that statement didn't make a whole lot of sense. For the time being, we'll just think of a transfer function as a mysterious black box, and when we apply an input signal into it, we get a modified signal out. And if we've designed this black box correctly, then it's a pretty good model of a real physical process. Let's take a completely ridiculous example to explain the benefit of transfer functions, and hopefully you'll get a better understanding of them in the process. Say you got in trouble at school, and you're asked to write your name 100 times on the chalkboard. But instead of standing right next to the board, the teacher says you have to stand on the opposite side of the room. And since you can't physically reach the board from where you're standing, you have to use this strange contraption. This consists of a flexible stick that has a claw attached to the end of it. And this claw moves a remote control, which drives a pair of linear actuators, that then moves another flexible stick, which is then attached to a piece of chalk, which finally is touching the chalkboard. And now you can finally start to write your name. I told you this was ridiculous, so just stay with me. If we take a simplified block diagram of this system, it might look something like this. The input into the whole system are your hand movements. This moves the first flexible stick that I'll represent right now as a black box, but start thinking of these as transfer functions. The output of this box is the position of the end of the first stick. The position is now the input into the remote control. The remote control, another black box, converts the position into an electrical signal in the form of changing voltage. This voltage is applied to the linear actuators, which converts the electrical signal into position again. This position is the input into the final flexible stick, whose output is the position of a piece of chalk, which finally draws on the blackboard. And if you've accounted for all of the relative motions in the system correctly, you can write your name 100 times and you get to go home. But how can you possibly even draw a straight line, let alone something as complex as your name, through such a flexible system with so many different transformations? The answer is by characterizing the behavior of each individual part, that is, each black box, and combining them to understand how the system behaves as a whole. And the simplest way to do that is with transfer functions. I'll finish this story in a bit, but first I need to preface what I'm about to claim with some background knowledge and just the smallest amount of math. We start, like most things in classical control theory, with the Laplace transform. What the Laplace transform does is map a function from the time domain to the S domain. I will describe the intricacies of the transform in a future lecture. However, for now I will write it here without any mathematical proof. As you can imagine, the Laplace transform is a complex operation in all but the simplest cases. Luckily, actually performing this integration is rarely needed because the most common transformation between time and the S domain are part of software packages like MATLAB, or can be easily looked up in tables, or even just memorized. Here are some of the more common ones. The Dirac delta function, which is a squiggly d of t, the Laplace transform is just 1. This is also the impulse function. Then you have x of t, the Laplace transform of that is just x of s. X prime of t, which is the first derivative of x, is s times x of s minus the initial position x0. Then there's x double prime, which is the second derivative of t, is just s squared times x of s minus s times the initial position minus the initial velocity. If you watched my video on linear time invariant systems, you know that any LTI system can be completely described by its impulse response. Just as a refresher though, I'll sum it up here. If you subject the LTI system to an impulse function, That's the Dirac delta function at time 0. And you can either measure or calculate the output, and this is called the impulse response of the system. But let's say you subject this to an arbitrary input. How can you determine what the output is then? Well, you can break that arbitrary input up into an infinite number of impulses. And since this is an LTI system, you can scale and shift through time the impulse responses appropriately, based on all of the scaled and shifted impulse inputs. Now, finding the system time domain response to the arbitrary input is as simple as summing up all of the infinite impulse responses. And since summing an infinite number of signals is impossible to do at one time, mathematicians came up with what is called the convolution integral. I'll explain using this block diagram notation. If you have an arbitrary input u of t, and you apply it to an impulse response g of t, then the output y of t is equal to the convolution of u and g, written here in integral format, or if you prefer shorthand, using this star, but these two representations are equivalent. So in this representation, g of t is the impulse response, and u of t is any arbitrary input. But here's what's great about the Laplace transform. If you take the Laplace transform of the input, which becomes u of s, and you take the Laplace transform of the impulse response, g of s, then the output y of s is just the multiplication of u and g. And g of s is the Laplace transform of the impulse response, which is called the transfer function. So we have reduced that difficult convolution integral with a much simpler multiplication step. Or more accurately, the Laplace transform is taking care of the convolution for you. To make sure that this sinks in, let's walk through this one more time, but this time with an example. Take a simple harmonic oscillator with mass m and spring constant k, which is subjected to an input forcing function u of t. It can be shown that the equation of motion of such a system is m times the acceleration plus k times the position, and that's set equal to the input u of t. Now to find the impulse response of the system, we set u of t to the Dirac delta function. And now let's solve this differential equation using the Laplace transform. To do that, we take the Laplace transform of the left side, which is m times the Laplace transform of the acceleration, which if we go back to our table, we can find x double prime. Now remember that there are no initial conditions for this problem, so we can set these to 0. And what we're left with is s squared times x of s. So if we go back down, we can replace x double prime of t with s squared x of s. Now we can do the same with the second term. We can go back up to our table and find that x of t is just x of s. That seems simple. So we get k x of s. Now we can take the Laplace transform of the right-hand side, which is just the impulse function, which has a Laplace transform of 1. From here, it's just a few algebraic steps to solve for x of s, which is the impulse response of the system in the s domain, which turns out is 1 over ms squared plus k. But what if we want this in the time domain? Well, all we have to do is take the inverse Laplace transform. And this isn't one that I've memorized, so I had to look this up in a table. And it turns out it's 1 over the square root of km times the sine of the square root of k over m times t, or a sinusoid, as you'd expect. But what if the input wasn't an impulse but a ramp function, u of t equals t? How would you go about solving what the response is to this input? Well, if you were in the time domain, you would do this through convolution. Or you would say you would convolve t with that sinusoid below. And this is a pretty difficult integration to do. Luckily, we can do this in the s domain by taking the Laplace transform of the ramp, which is 1 over s squared. Then to find the response to this ramp, all we have to do is multiply 1 over s squared by 1 over ms squared plus k. And remember also that 1 over ms squared plus k is the impulse response to the system in the s domain, so this is the transfer function. And notice that we got this transfer function by taking the Laplace transform of the equation of motion. We never needed to go to the time domain. So now that we know that, let's get back to our example above. If we were able to write the equations of motion for each of these individual processes, then by the method described below, we would have the transfer functions, which we could insert into all of these unknown black boxes. For example, the sticks could be modeled as an inertialess spring and damper. This has a transfer function of 1 over Cs plus K. The remote could be modeled as a second-order process as it converts mechanical position into electrical voltage, and the linear actuators could be modeled as a mass. So now what would have been a near impossible set of integrals if we had tried to do this in the time domain with convolution, combining these transfer functions in the S domain is as simple as multiplying them all together. And the result is the transfer function of the entire plant, where the input into the plant is your hand motion still, and the output is the chalk position. So hopefully you can see how important transfer functions are to modeling a control system. In the lectures on frequency response and open loop and closed loop performance, you'll see that there are many other ways we use transfer functions. The last thing I want to leave you with is just something to think about. This is actually a closed loop system that you, the troubled student, is part of. The reference signal is your name. This is what you want written on the chalkboard. You sense the current state of the system with your eyes, and you compare what you're seeing to what you want written. Your brain interprets these errors and generates commands to move your hands. But what if you wanted to remove yourself from this control loop and turn it into an automatic control system? We'll discuss that in future lectures.